Okay, so today we will be discussing another randomized algorithm that is called this quicksort. Okay, quicksort, randomized quicksort. Okay, so let us motivate that why this randomized quicksort is necessary first. Okay, so first we have to motivate ourselves that a randomized quicksort algorithm is necessary. Okay, that is very important. Okay. Now, for this, we have to know what the quicksort is all about. Okay, without randomization. Without randomization, if we do the quicksort, then how it is performing. Okay, so that we have to first know, and then we have to come to the point that randomization is necessary. Okay, so say take a list of numbers in the array A, and this array A is to be sorted. Okay, so this array A having these numbers 2, 10, 8, 12, and 9. So 2, 10, 8, 12, and 9. So this is array. Okay. We are having this array. This is the index position 1, 2, 3, 4, 5. Okay. So array A1 is 2, A2 is 10, like this. Okay. And now in the quicksort, what we do is we choose a pivot. We choose a pivot element, and that pivot element in iteration after iterations, that pivot element, which place we have to choose as the pivot, that will be remaining fixed in deterministic quicksort, not the randomized one. The general quicksort that we know, what it does, it is fixing a pivot first. Okay, so say the first element as the pivot or the last element as the pivot. In CLRS, they take, in deterministic quicksort, they take the last element as the pivot. Okay. So now this we have to fix the pivot, and this could be the first element of the array, or the last element of the array, or the middle element of the array, and so on. Okay. Now the thing is that say if we set the last element of A as the pivot, that is A5 equal to 9, A5 equal to 9, we had this A5 equal to 9. Okay. So this A5 equal to 9 we are having. So if we are fixing that element as the pivot, then in our example, this we assume that A starts from index position 1. Generally, in implementation, what we do, we start the array index position starts with A0. Okay. Right. But here we are assuming that array index position starts with 1, A1. Okay. Now, in the quicksort, what we got to do around that element is the pivot element. Okay. And that pivot element is to be compared with every other element. Okay. So now this pivot element we are having, say 2, I guess 10, 8, whatever, say 12 and 9. Now this guy will be compared with this 9, and as this guy is less than or equal to 9, maybe we are taking it, so this is the 9th position, and we are taking it in the left side. Okay, then 10 is greater than 9, so it will be in this position, say in the right side. কোন ছেলেটা? ও আচ্ছা আচ্ছা। না আমি 12:30 থেকে আমার 1টা থেকে এখন ক্লাস চলছে, তো 12:30 থেকে 1টা অবধি ফ্রি থাকবো, 1টা থেকে আবার ক্লাস আছে। হ্যাঁ 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 ঠিক আছে, আমি চলে আসছি সবাই। ওকে okay, so what we got to do, then we have to compare this 10 with 9, and as it is greater than, so it will be going uh, right side of 9, and 8 it will be coming left side of 9 here perhaps, okay, and then 12 will be in this side, okay. So this all other elements we have to compare with this guy, okay, and then we have to measure that whether this guy is coming in the right side of that element or left side of that element. Okay. So this around 9, if I am partitioning, so this is called the partitioning process. Okay. So this partitioning process is giving that this is the left side of this array and this is the right side. Okay. This is the right side. And then what we got to do is, so this 9, you see, this 9 is placed, in its proper place. Okay, so if I sort the array, then you see it will be coming 2, 8, 9, 10 and 12. And this ninth position is at index position 3. Okay, and this is perfectly placed. Okay. So that each time I am taking the pivot, that pivot is perfectly placed in some order. Okay. So this 9, and then you see this 2 and 8 is like this, and 12 and 10 may be like this. So it may not be sorted. This left hand side and right hand side may not be sorted. Okay. And then what we got to do, we have to take this left side and do the same procedure. In the left side, say 2, 8. So if I am having say 17 elements, so in this side maybe 5 elements, something like that will be there. So that 5 elements again we have to after say these 5 elements. So this guy will be chosen as the pivot, and then around that pivot we have to partition the elements. Okay. And this right side also will be having the remaining elements. So in that case, the right side also we have to choose the pivot last element, and then around that pivot we have to partition the right side into 2 parts again. So this process will continue until and unless the array size is becoming too small. Okay. So this is the partitioning process, which will be doing a great thing for placing that pivot into its proper place. Okay, right. So this is the way this quick sort we implement. Okay, right. Now the thing is that the main problem is that, okay, if we fix the pivot, then there might be some problem. Okay, say 2, 8, 10, 12, 18, something like this. Say if the array is already sorted, and if I am choosing this this element as the pivot all the time, right? Then around this we have to partition the elements. So you see these 2 will be placed here, and then all these elements will be coming in the right side of this guy, and the left side of this will be empty. So we'll be having 0 elements here in the left side, and all other n minus 1 elements will be in this side. So in that case, this side, as we have seen after partitioning, we have to solve this leftmost partition recursively and rightmost partition recursively. Okay. So if I am having n minus 1 elements here in this right side, so the recurrence will be looking like this. We are having Tn, and in one side we are having Tn minus 1 elements. In another side we are having T0 elements. And then this partitioning process will be taking this theta n time or order of n time. Okay. So this T0, if I am assuming, okay, T0 is some constant, okay, or maybe T0 is 0, nothing is there to solve, then it will be boiling down to, even if I am taking a constant, this constant will be subsumed to this theta n, and the recurrence will be coming like this, Tn minus 1 plus theta n. Okay. Now if we solve this using, say, substitution method, okay, then it will be coming, the answer is Tn equal to theta n square. Okay. So that's why we say that, okay, the worst case running time, running time of quicksort is this theta n square. Okay. Are you with me? So now the thing is that we have to chant the mantra that can we do better? Can we do better? Okay. Yes, we can do that. The thing is that we have to utilize this randomized algorithm. We have to have this randomized algorithm version of quicksort, and its expected running time as we have seen that we are dealing with some expected case, okay, expectation. We have already dealt with expectation in hiring assistant problem. In an expectation means what is the performance of the algorithm. So this expected running time will be boiling down to this order of n log. Okay. So that we have to prove. Okay. And what do we mean by this randomized process in this quicksort implementation? That we will be discussing now, and we will be proving this. It will be a lengthy discussion. Okay. The analysis is easy, but it's algebraic manipulations. We have to have some patience to grab all these things. Okay. So pay your attention. I guess I'll be getting your attention. Okay. Right. So we have motivated that, okay, if I fix the pivot, then we'll be needing theta n square time or order of n square time, worst case behavior of this quicksort. But we can do better by randomization. Can we have a deterministic, this is exercise, deterministic algorithm for quicksort with order of n log n time. I guess yes. Whether you can find that one also. You think of it. You can take the help of this kth smallest element finding algorithm as a subroutine. Okay, kth smallest element finding as a subroutine. This is the hint I am giving. Think of this, that whether this is possible or not. If Google is coming in the campus interview or Facebook, they might be asking this question. Okay. So this randomized algorithm that we'll be discussing right now is relying on this simple, very simple idea that instead of fixing the pivot, we can randomly choose the pivot. Okay. Just like we interviewed the candidate in a random order. Okay. So you have to say 2, 10, 9, 8, 5, something like this. If the array is like this, then you can choose the pivot randomly. Maybe I can choose the pivot randomly and it is coming as 8. Okay. So in that case, it might be 2, 5, 8. 2, 5 is less than equal to this 8, and 10, 9 will be here perhaps, okay, the right side. So you are having some kind of partitioning which is looking like balanced. That is the main idea of randomized quicksort. Okay. What we got to do is, whenever we are fixing the pivot and the adversary that means the data which is coming from the third party. Okay. What they are giving the data in an ascending order, and you have to sort that ascending order list into again the sorted order. Okay. So quicksort as a dumb algorithm, it will not be having any kind of idea whether the data is sorted or not. Okay, it will be running its algorithm, and ultimately that will be produced. The output will be produced as a sorted one. Okay, but it was already sorted. Okay. So this we have seen that if this is 2, 5, 8, 9, and 10, and we are fixing the pivot here, then we are having 2 is here and all the other elements here, and this guy having 0 elements. Okay. This side. So this is not a balanced partition. So there lies the problem. There lies the problem that, okay, deterministic quicksort, if we are not taking a very good care about all those kth smallest element finding algorithm and all these things, if we are not taking into consideration, if we are implementing it simply, then the worst case behavior will be very bad. Okay? Because every time I have to recurse to a list, to a sub list, which is having uh, bulk of the elements. Okay? So that is, there lies the main bottleneck, and we have to eradicate that bottleneck. And to eradicate that bottleneck, the randomization is one of the most viable options. Okay? So now this we have got this algorithm that, okay, randomly select the pivot. You have to randomly select the pivot. So here randomizer will be in use. So that's why it is a randomized algorithm. As we define the randomized algorithm, that along with the input, we need a randomizer to help improve our efficiency of the algorithm. Okay. And then other thing will be remaining exactly the same. Okay. After choosing the pivot, we have to do the partitioning process, and then it will be going just like the deterministic quicksort. Okay. So only change we are doing, and it's a big change, that we are choosing the pivot randomly. Okay. Right. No other change is there. And I will be telling everybody must be implementing this quicksort. এটা নরেন কুইকসর্টটা পোস্ট করে দেবে এক্সারসাইজ হিসেবে quicksort deterministic and randomized, both you should implement, and you should post it. We'll be posting as an assignment, and you will be submitting that assignments online. Okay. Implementation in Python. Implementation, obviously. Okay. So now we have got a randomized algorithm, and the thing is that the expected running time of that algorithm, we need to prove that it is order of n log n. So now we are going to the analysis part. Okay. And here we will use this indicator random variable. Indicator random variable we will be using this indicator random variable again. Okay. So let us see how the indicator random variable is coming into picture here. Okay. Now we need to observe something here. Say take an example array like this 2, 10, 8, 12 and 9. Okay. And whenever I am choosing the pivot randomly, okay. So if the array is 2, 10, 8, 12, 9, if I am choosing the pivot randomly, then this guy or this guy or this guy or this guy or this guy, anybody can be selected as the pivot. Okay. Right. And now say k equals to 1, that is the first smallest element as the pivot is chosen. Okay. First smallest element. We don't know. Okay. Whenever I am choosing the pivot randomly, whether the first smallest element will be coming or the second smallest or third or fourth or so on, which one will be coming, I don't know. I don't know. But it may be the case that, okay, first smallest element is coming. Let us suppose that first smallest element has come up. Okay. Whenever I have chosen the pivot randomly. Okay. Now, if the first smallest element is chosen as the pivot, then what will be happening? So this guy, this 2 is the first smallest element out of these elements. Are you getting? Are you getting? 2, which is the third smallest element here. Third smallest element. 9. Yes. So now if 2 is taken as the first smallest element, and then we have to partition around this pivot. Okay. We need to partition around this pivot. Then again, what will be the recurrence? It will be coming. So 2 will be here and all these elements will be here. All these 10, 8, 12, 9, all these elements greater than these 2. And this side will be having 0 elements. So if the randomizer is choosing 2, that is the first smallest element as the pivot, then the recurrence we need to solve will be of this form. Tn of this form. Tn equal to Tn minus 1 plus T0 plus theta. Is it the case? Okay. Now that it is here, I am choosing the pivot random. So first element may be chosen as the pivot, or the second element, smallest element, might also be chosen as the pivot. So 8 might be chosen as the pivot. If 8 is chosen as the pivot, then the recurrence we need to solve will be of this form. If 8 is here, then 2 will be here and 10, 12, 9 will be here. Okay. So one element in this side, rest of the elements in this side, and 8 is here. Okay. Right. So then the recurrence will be n minus 2 elements will be in this side, and then one element will be in this side, T1, plus this theta for partitioning process. Okay. So likewise, it will be going on. It will be going on, say, then if third element is chosen as the pivot, then it will be Tn will be equals to, in this third element, then two elements will be here, okay. So it will be Tn minus 3 plus T2 plus theta n and so on, okay. So now what we are doing here, this is some kind of case statement. If first element is chosen as the pivot, this will happen. If the case 2, if the second element is chosen as the pivot, then this will happen. Okay, right. This we need to recurse in this. We need to solve this recurrence, right? So choosing each smallest element, we can think of this is a simple single experiment. Okay. So we can think of that, okay, the first smallest element, whenever I am choosing, so this is a single experiment. The second smallest element, this is another single experiment. Okay. Now we should consider a random variable for this using the concept of indicator random variable. And what we have got that we are having some case statement. If this happens, then this recurrence. If this happens, then this recurrence. So this case statement can be mathematically formalized by using indicator random variable very easily. So that we are going to do right now. Okay, so let us. So what we will be doing is this Tn. This Tn is the random variable. It may take several values. Okay, and it may have this recurrence to be solved Tn minus 1 plus T0 plus theta n, or Tn minus 2 plus T1 plus this, all this. So Tn could have so many values. Okay, and what we will be doing, we will be summing up all this and we will be taking the expectation of that random variable. So what we are doing for analyzing this quicksort, we are thinking that, okay, if first element is chosen as the pivot, then what could be the structure of the recurrence? If second element is chosen as the pivot, then what could be the structure of that recurrence to be solved? Okay, and what could be the cost? So if first element is chosen as the pivot, if we solve Tn minus 1 plus something, then we will be having some cost. If second element is chosen as the pivot, then some cost will be there. So what we are doing is we are thinking each of these recurrences whenever I am solving. So each of these is a single experiment. So this is something like we are looking for this x, that is our Tn. That is summed up of x1 plus x2 up to xn. Okay. And then we are taking the expectation both sides, we will be getting the expectation of Tn, expectation of x. Okay. So all those costs which could be incurred for quicksort, whenever I am choosing the pivot randomly, all those costs I am considering and I am taking the average. So that is the idea of analyzing this quicksort in an expectation. Okay, so that is the idea we are taking here. There is another, we do it in some other classes, and that is also in first edition of CLRS book. This is the way they analyzed. Okay, then in the second and third and fourth edition, they are analyzing it differently. That I take in randomized algorithm class, but this is a more general technique that is utilized in CLRS in many different situations. So that's why I am taking this general approach here. Okay, you should be going to CLRS book for another implementation, and if you are not getting it, you can come to me, okay, offline. But this is a general idea that we use, that CLRS book is utilizing in several different algorithms. Say for randomized kth smallest element selection problem, say randomly built binary search tree problem, and so on. Okay. They are utilizing this technique. Okay, this if the randomized kth or smallest element selection problem will be almost having the similar thing. Okay, so I can choose the pivot randomly. Okay, so if the first element is chosen as the pivot, then what will be happening? If the second element is chosen as the pivot, what will be happening for kth smallest element, randomized one? So like that way, we have to sum up all this cost, and then we have to take the expectation both sides. Then we will be getting the average case almost not exactly we should be telling average case, but on an average what we will be having, that will be having with this expected analysis. Okay. So now say what is the time? So for case K, we are having several cases happening. For case K, we can define one indicator random variable as follows. Xk, so this Xk is the indicator random variable, and that indicator random variable is associated with the event that kth smallest element is chosen as the pivot. Kth smallest element is chosen as the pivot. And this will be, if that element is chosen as the pivot, then it will be counting 1. Yes, it is. Okay, if it is happen. If happens, 0 otherwise. Okay. Right. So now, with this definition, we can transfer that case statement. If k equal to 1, then this will be the recurrence. If k equals to 2, this will be the recurrence. We can channelize that English statement into mathematical formulas or mathematical expression like this. Tn will be equals to, so Tn is equal to summation k equals to 1 to n xk. So this is the indicator random variable, and this will be having k minus 1 plus Tn minus k plus theta n. Okay. So everything within this bracket, right? Now check whether it is exactly aligned with our case statement or not. So if k equals to 1, then it is x1. That means the first element is chosen as the pivot. If the first element is chosen as the pivot, then what will be tk minus 1? That will be k is 1, so it will be t0. And tn minus k, that will be tn minus k, that means tn minus 1. Okay. So it will be tn minus 1 plus t0 plus theta. If k equals to 2, it will be t1 plus tn minus 2 plus theta. Okay. So what we are doing, we are considering all possible cases, all possible recurrences, what we could have to solve, right, as far as choosing the pivot is concerned. Okay. And we are summing it up, right, and then we'll be taking the expectation, then we'll be getting the average. Okay. So that is the main idea of analysis. So this expression forming is very important. Okay. Once this expression is formed, then what we got to do, we have to analyze this. We have to analyze this algebraically. And that is not so difficult, little bit tedious, but if you follow, then you can get it. So now once this equation is formed, we have to perform routine algebraic manipulation. So we have to take expectation both sides. We have to take expectation both sides. Okay. And before solving that, one thing you have to notice that, okay, if I am having 2, 8, 10, 9, 12, something like this, if there is like this, then I am choosing the pivot randomly. So what will be the probability that this guy will be chosen as the pivot, or what will be the probability that this guy will be chosen as the pivot, or this? It is equally likely case because we are choosing the pivot randomly. Okay. So anybody can be chosen as the pivot. So if I am having n number of elements, if I am having 5 elements, then what will be the probability of choosing this guy? 1 by 5. What will be the probability of choosing this guy? 1 by 5, and so on. All these will be having 1 by 5. If I am having n elements, then out of these n elements, one element will be chosen as the pivot. What will be the probability of that? 1 by n. So xk will be equals to 1. Okay. Xk. That means kth smallest element is chosen as the pivot. That is 1. What will be the probability of that? So that is 1 by n because it is equally likely. Okay. And another thing is that I have chosen a pivot. I have chosen a pivot, definitely. And around that we have partitioned the element. We have partitioned the element n minus k plus t k minus 1 plus theta. Okay. Right. Around that we have done a partition. But after that, what will be how I will be recursing here, or how I will be solving this guy or this guy. Okay. Right. So there is no, I mean, that previous whatever we have chosen as the pivot, then that pivot will not be having any control, that it will not be dictating that how this n minus k will be further be solved. Tk minus 1 will further be solved. Okay. This is not dependent on whatever we have chosen pivot previously. This solving. Okay. After choosing the pivot, we have got this. But after that, how this t n minus k or tk minus 1 to be solved, that pivot will not be dictated. Okay. So that means that choosing the pivot, this xk and this random variable, okay, will be completely independent of the others. Okay. So this is necessary because whenever we are having this, we have got this x1 plus x2, say simplified one, and then by linearity of expectation we have got it is expectation of x1 plus expectation of x2, and in this case x1 and x2 may be dependent also. But if I am having x1 x2, and if I have to write it is x1 the multiplication case, expectation of x2, it is multiplication of the individual expectation by linearity of expectation. This formula is also valid, but valid when x1 and x2 will be completely independent. Then only this multiplication rule we could apply. But here this addition rule we can apply even if x1, x2 not independent. Okay. So this you have to remember. So that's why we have seen that we have got xk and then it is multiplied with some other random variable. And that some other random variable, we are taking xk, we are trying to apply this, we are having this form, x1, x2 form. This xk is one random variable and this inside this is another random variable. And we will be separating it out in the next step. Okay. So we have to argue that this xk and this thing are completely independent. Then we can apply this multiplication rule of separation. That means the linearity of expectation on multiplication case, multiplication of the random variable we can also apply. So that's why we have argued that this xk and then this thing, whatever inside, is completely independent. Then only we can proceed further. So how to proceed further we'll see in the next class. So next class will be needing some kind of analysis again, and then In the later part, we will start another randomized algorithm, that is randomized min-ka.